Welcome to Center of Math's series on graph theory. Today we're going to talk a little bit about Eulerian graphs. So first a multigraph. So first we're going to define multigraph. Multigraph is just a graph where the vertices can have multiple edges between them. So instead of just one edge, you can have as many edges as we want between the vertices. An Eulerian graph is something where we have is a graph where we have a circuit that goes through every edge exactly once. So it begins and ends in the same vertex, and every edge has gone through once in some path, some trail. So a theorem we can prove a theorem that gives a necessary and sufficient condition for a graph to be Eulerian is this one, saying that it's Eulerian if and only if it's connected and has only even degree vertices. So we can prove this. First, assume the graph is Eulerian. So first, let's assume it's Eulerian. So we have a circuit going through every edge in the graph once. And now let's assume, and so clearly this has to be connected, otherwise we wouldn't be able to get through every edge, starting on one vertex and going to every other vertex. So yeah, clearly we need the connected condition. Now assume if we had, say, and also we know from our previous theorem we have to have an even degree of odd vertices, so we can have 0, 2, 4, 6, etc. odd vertices. So assume we have at least two odd vertices, and at least 3 or more vertices in our graph. So So since our graph goes through every edge once and we're connected, we're going to visit each vertex at least once. So we have some trail, some sequence of vertices for our trail. And so really in this trail we can start anywhere because we go through each vertex at least once, so we can say we start on that vertex and just continue the trail from there. So assume we start outside these two odd vertices. Now the thing we want to note here is because we have say we have two odd vertices, they're connected to some vertices other than themselves. So note, once we enter the vertex, we go through one edge. Once we leave, we go through two edges. Once we enter again, we go through 3 edges. Once we leave, we go through 4 edges. And the thing we're concerned about here is if we're outside the odd vertex, we've gone through an even number of its vertices. If we're on the odd vertex, we've gone through an odd number of its vertices. And so for an odd vertex, for us to go through all of its edges, starting outside of it, we have to end on the odd vertex. And if we have 2, we have to end on 2 odd vertices, which is clearly impossible, and so we cannot have 2 or more odd vertices. And if we have 2 vertices, it's easy to check that case. So now let's assume we have a graph that's connected and only has even vertices. So first thing we're going to do, we're going to start on some vertex. We're going to make some circuit going away from that vertex and coming back to it. Note, if in our graph, note we can make such a circuit, a trail that goes through, doesn't repeat edges and comes back to our same vertex. We can make this because assume we couldn't make this. So that would imply at some vertex we cannot keep going. We get stuck at some vertex. But from our previous observations, if we end on a vertex starting outside of it, we've gone through an odd number of its edges. And since every vertex has an even number of edges, we can't end on a vertex other than the one we started on. We can't get stuck outside. So clearly we can make some circuit starting at a vertex, ending at a vertex. And the second thing we want to note, so we take some circuit starting at a vertex, ending at a vertex, and we want to build up this circuit with a strictly bigger circuit, and we can keep doing this, repeating this method until we get the whole thing. And so we're going to make this strictly bigger circuit, but note since our graph is connected, we did not take all the edges. Clearly there's a vertex, which some unused edges, some edges we did not go through, like consider the sequence of vertices A0, A1, A2, A3, A4, A5, back to A0. This is a trail. It takes these edges in this hexagon only once. But note, So our graph is connected. We did not take all the edges. And because our graph is connected, we're going to have at least one vertex here, which has some unused edges on it. Otherwise, if we had unused edges and none of our vertices, if we use all our edges in the vertices we met, that will imply there are some edges outside that connect other vertices or not. It would imply the graph is disconnected, which we don't want. So that means if our trail did not take up the entire graph, we have some edges on the trail, some edges connected to vertices on our trail, which we could then append to our trail. And we do this by, we pick the vertex with the edges attached to it. We then do the same thing, pick some trail on this vertex, and we ignore all the edges we already used. And we know that once we take out all the edges from the graph we already used, we still have a subgraph with an even number of edges for each vertex. And so for our vertex that still has edges, we can take this vertex, we can go through the edges that are connected to it. All the vertices still have even number of edges, so we can do the same thing, and we can strictly grow our circuit. And so then we can repeat this as many times as we want, and so we have a strictly increasing sequence of graphs whose size is strictly increasing, and clearly we're going to get a circuit that includes every edge of our graph repeating this process. And so that would show us, because we can do this for an arbitrary graph that's connected and has any vertices with only an even degree, with only even degrees. We can do this for any graph. And so a graph that's connected and only has even degree vertices is Eulerian. Yeah. So one example of an application of the theorem, the Königsberg bridge problem. It's a famous example of a not Eulerian graph, because you can see this vertex right here has 5 odd degree coming through it, these 2 as well. All 4 of these have odd degrees. So we do not have an Eulerian graph here. And this is a famous example. This Euler first proved the previous theorem, I believe, from concerning this graph of trying to cross each bridge in this town of Königsberg. And it's impossible. Yeah. Thanks for watching. Please check out our other graph theory videos. Check out centermath.org. Follow us on Facebook and Twitter. Thank you.